Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Delighted to have Vishy here today from ANU, Australian National University, at which he's an adjunct research fellow. He's also a principal researcher at NICTA. So I went online to find out what NICTA stands for, and the NICTA webpage says it stands for National ICT Australia, which with some help. So then I went to Live, which sent me to the to the NICTA homepage. So then I went to Google, and that said it was the National Insurance Crime Training Academy. Presumably you go there to learn how to be a good criminal in insurance. So then Wikipedia, finally I found the answer. The ICT stands for Information Communications Technologies. So NICTA stands for National Information Communication Technologies Australia, I believe. Of course I could have just asked Vish. Vish is just here, he's leaving tomorrow, so if you want to catch him, now's your chance, this afternoon after the talk. And you may not know this, but he was a developer at Microsoft for a year. So he has quite a lot of experience in actually, product group stuff. It's a very interesting range of work he's been doing. And today he's going to talk about graph kernels.
Thank you very much. So basically today I wanted to talk a bit about work that I've been doing on and off for the past couple of years with my student Carsten Borgward, who's now at Cambridge, Nick Stroud, my colleague, and Rishi Kondor, my friend and collaborator. Currently at Gatsby. So I guess to this group or to people at a research lab, I don't really have to introduce why you need to work with graphs. I mean, graphs are really a very natural way to work with a variety of representations, and things like if you look at the internet, you can model each page as a node in a graph, and you can also model things like proteins as graphs naturally. You can model interactions between people in a social network as graphs. There are tons and tons of examples of graphs that occur all the time in real life. And two types of questions that frequently get asked when you are working with graphs, at least when you want to do some kind of machine learning or learning on them, is the notion of how similar are two nodes in a graph. So how do you somehow respect the topology of the graph and yet find out whether two nodes are similar or not? This is a common question that you would want to ask. And the other question that you would want to ask is things like, if I give you two graphs, how similar are these two graphs? I mean, are these two graphs, how can you figure out that if they're similar or not? And today I'm going to talk about some ideas on how these two things can be done, how these two questions can be answered, and also hopefully provide you some kind of motivation on how these two questions are intimately related and can sort of be addressed by a common framework. So that's essentially what I'm going to talk about. So before I actually go on and talk about how you would actually go and compare graphs, I need to introduce some amount of notation and set some common ground for us to talk about things. So of course when I mean a graph, for the rest of this talk, just for simplicity, I would always assume that it's an undirected graph. You can also, many of the things that I'll talk about also works with directed graphs, but things get a bit more complicated and I just want to keep it simple. The other thing that you'll notice is that I generally try sort of implicitly assume that I'm working with unweighted graphs, so there are no weights on the edges for now. Again, this is only to get the main ideas across. Almost everything that I talk about will translate to weighted graphs, so just keep that two things in mind. And so basically a graph is described by its vertices, a set of nodes, and then edges which interconnect them. And another equivalent representation of a graph is in the form of an adjacency matrix. So basically an adjacency matrix, does this work? How does the, no, which button here? No, it doesn't? No, sorry. least I figured one thing. Generally technology challenged with these things. I see. So I could continue using the mouse. So basically, an adjacency matrix is just a matrix of zeros and ones. Of course, if you have a weighted graph, instead of just having ones, it has the weights in it. And basically two nodes, say 1 and 2 are connected, and so at position 1, 2 there is a 1, but on the other hand 1 and 3 are not connected, so there's a 0 here. So this is just a very simple, extremely simple thing almost everybody knows about an adjacency graph, adjacency matrix. And of course a subgraph of A is just a smaller set of vertices of the graph and the corresponding edges, and essentially a submatrix of this matrix corresponds to a subgraph. So this is extremely straightforward. And another matrix that I'll work with is the so-called degree matrix. Again, it's an extremely simple matrix. It's a diagonal matrix, and at each entry it tells you how many edges are incident upon that node. So for instance, 1 has 2 edges incident upon it, so it has 2. Well, on the other hand, 3 has 3 edges incident upon it, so it has a 3, and so on and so on. And one thing that I would do often is that I would normalize the adjacency matrix. So instead of just working with the plain adjacency matrix, sometimes I might want to normalize it, because the advantage of doing this is that it becomes a stochastic matrix. So I can talk about random walks, which I'll introduce shortly. And the third matrix that's associated with a graph, in which graph theorists, especially there's a whole field in graph theory which studies these, are the people who study the spectrum of a graph, and they work with what is called a graph Laplacian. So the graph Laplacian is basically the degree matrix minus the adjacency matrix, and you can also of course normalize the graph Laplacian by decorating it on both sides with d to the minus 1/2. The reason for normalizing is generally would be so that you can bound the spectrum. So the spectrum gets bounded between 0 and 2. Without this normalization, you can't say much about the spectrum. So the spectrum could be unbounded. And another key notion that I'll use throughout the talk is the notion of a random walk. So what's a random walk? Exactly what you would expect. You're sitting at a vertex, in this case at vertex 3, and you ask the question, which vertex can I jump to? Of course, the vertices that you can jump to are the ones which you're connected with, right? And then you can choose them with a certain probability. Typically the probabilities will be proportional to the weights of the edges connecting that vertex to all its neighbors. So if a particular vertex is connected with a stronger weight to its neighbor, then there's a higher likelihood that you will choose that vertex. And this is just formalizing that intuition, that the probability depends on the normalized adjacency matrix. Now, if you are told, if I give you a graph and I tell you find for me or count for me all the walks of length 2, how can you do that? There's a simple trick, and this is a very key insight actually. This is an insight that I'll use for most of the talk. There's a very simple trick. If you take the adjacency matrix and you square it, so you multiply the adjacency matrix with itself, then you can see that it counts the number of all 2 length walks between any 2 vertices. Between any vertex I and j, you can count the 2 length vertex by just looking at the corresponding entries in A squared. So in that sense, you can think of the adjacency matrix as saying what are the 1 length walks between any 2 vertices, and A to the k tells you what are the k length walks. So in this case, A squared tells you what are the 2 length walks. So you can do this inductively and do it for any k. So for instance, here 1 and 3 were not originally connected in the graph, and there was a 0, but here at 1, 3 there's a 1 because they're connected by 2 length walk. There's only 1 walk, you can check that. And of course, similarly, if you look at the A twiddle, which was the normalized version, which was a stochastic matrix and had the probabilities in it, then the entries of A twiddle square are basically the probabilities of reaching from I to j by taking a 2 length 2-step walk. So if somebody gives you a graph and says, okay, here is a nice little graph, and find for me how similar vertices are in this graph. So if I give you any pair of vertices, you have to return back to me a number. The number must be high if they are similar and must be low if they are dissimilar. Then one possible idea, given all the stuff that I talked about, you could do is that you could count how many walks exist. Say, if I want to again compare 1 and 3, I could compare how many walks exist between 1 and 3. Right? So I could just count the number of walks, and I say if there is a lot of walks which connect these two vertices, then somehow the two vertices are very close to each other, and if they are not, then they are dissimilar. But this simple idea, there's a problem. What's the problem? To illustrate the problem, let's say I want to count the number of vertices, the number of walks between 1 and 3, right? So of course there is one walk which goes 1, 2 and 3, there's another walk which goes 1, 7, 8 and 3, but then I could do 1, 7, 6, 5, 4, 8 and 3, and I can keep looping in 6, 5, 4 infinitely and then go to 3. So for those of you who are familiar with traditional computer science or formal methods type stuff, this is roughly what they do in the pumping lemma to show that certain automata can accept infinite length strings, is basically by saying if there is a loop, then you can keep infinitely looping in that string to pump the weight of the automata. So then this seems like a dead end. If the graph has cycles, then you get infinities, and this is not meaningful. Yes?
What do you mean when two nodes are similar? I can think kind of similarity, like two nodes can be similar because there are three edges going from those three nodes. That notion of similarity is different than the similarity you're talking about.
Yes, so I'm just saying similarity in a very abstract sense of saying if two nodes are similar, then you should return to me a higher number, and if not, they should be a lower number, and I sort of give you the freedom to respect the topology of the graph and give me back a number. So you could respect the topology of the graph by saying, okay, I just count the out degrees, and if the out degrees are the same, I return you a high number, otherwise not. But that kind of seems like you're only looking at it locally. Yeah. But this is more global because it takes into account the overall graph structure. So, and basically what I'm driving towards is to get into what is called a kernel, which is basically where I want to get at. So here is a different idea. You could say, well, really what I'm interested in is that short walks should have a large weight, while as you take a longer and longer walk to reach from I to j, then I should discount the walks, right? And so if I appropriately discount the walks, then it is possible that I can actually find a meaningful measure of similarity. I'm kind of dumbing things down a little bit when I say you have to choose it appropriately. It depends on the spectrum of the adjacency matrix. Essentially, you have to ensure that as you take the powers of the adjacency matrix, the spectrum basically is trying to push things up, and you have to decay them at a rate faster than the spectrum of the adjacency matrix in order for things to work. So this is what I mean by appropriately. But then this kind of seems like a natural idea that if two nodes have a lot of short walks that connect them, then they must be very similar. But if you have to go through a lot of nodes to connect two graphs, then they are dissimilar. One kind of discounting factor, I mean this is not the only one, I'll talk a bit about others. One discounting factor that you might want to work with is a discounting factor which looks like this. So you just choose a decay factor lambda, which is actually there's a typo, it must be strictly less than 1 and also strictly greater than 0. So you take a discounting factor which is between 0 and 1, and you downweight it by the factorial, the k factorial. And now if you look at the notion of similarity, you say that I and j, two nodes in the graph, are similar to each other if the ijth entry, which corresponds to this matrix, is large and it's small otherwise. And if you just stare at it for a minute, you'll immediately see that this is nothing but the exponential of the adjacency matrix. Condor and Lafferty in 2001 or 2002 came up with essentially the same idea. They had a different motivation. They came from Gaussian processes and infinitely divisible distributions, and instead of working with random walks, which are in some sense discrete time events, so you take discrete time steps, they worked with a diffusion process. So a diffusion process in some sense is a very natural kind of random walk, where at time step, so think of the following process, that at every time you retain some alpha portion of the weight to yourself, and the rest of the 1 minus alpha you distribute to your neighbors. So this happens at every time step. Then instead of doing it at every time step, you say you do this infinitesimally often. So this is like saying that you're compounding some interest not just at discrete times but infinitesimally often, and then you would see that you would end up with exponential. So essentially that is where they came from, and they were talking of doing this diffusion and then passing weights infinitesimally often to their neighbors, and so and then they came up with this expression for a kernel. And of course they can show that this is a valid positive semi-definite kernel. So for those of you who are not machine learners, in machine learning people care about a meaningful measure of similarity which they can plug into an algorithm at some point and actually learn things out of that. And one of the nice mathematical things that you require there is that you need to be a valid positive semi-definite kernel. Yes?
Is there any sort of intuitive way to think about the feature space in which the kernel is built on?
For this case, you can think of the set of all. Not for the diffusion kernel on the nodes, but for if you do the same thing on the two graphs, then there is an intuitive way, but not for. I don't know of an intuitive feature space for the diffusion kernel itself. And then, of course, in 2002 or 2003, Condor and Smola basically observed that, what Rishi and Alex observed is that the Laplacian has a very special property. It, in some sense, measures the variation of a function along the graph, the edges of the graph. So this is something that's much closer to what people in spectral graph theory would use, the fact that the Laplacian measures variation. So if you have a function that varies a lot across two nodes that are connected by an edge, then you'd get a very heavy penalty because this term would be very high. On the other hand, if the function was high at different places but across edges which were connected, if the function was not varying too much, then you'd get a low value for this. So basically F transpose LF is in some sense a measure of the variation of the function, how much the function varies. So one intuitive idea is that you can use this to regularize. So if you want to learn some kind of a function on the graph which is smooth with respect to the Laplacian, then you can use this as your regularizer and say that this is a penalty, right? So every time if the function is completely uniform, then you can see that this value is 0, but if the function varies a bit on the graph, then you get some penalty, but on the other hand it might be minimizing your loss. And then they observed that instead of just regularizing with the Laplacian, you can change the regularizer by essentially changing the spectrum of the Laplacian. So this is a deep theorem that they proved, that basically all the forms of regularization that you can implement in a discrete space essentially can be done by taking the spectrum of the Laplacian and applying a transformation to it. So all that matters are the Laplacian and all the spectral functions on the Laplacians if you want to ever regularize in discrete space, and that a wide variety of decreasing functions. Yes. So the R's are the L's are the eigenvectors and the rho's are the eigenvalues of the Laplacian. Sorry, I forgot to mention that. And then, of course, the diffusion kernels fall out as a special case because they are just the ones where you choose to exponentiate the spectrum. So it's well known that the exponential of a matrix is basically nothing but the eigenvalues with the eigenvectors with the eigenvalues exponentiated. And then you can also choose other kinds of decays, and then you can do a p-step random walk where you stop your random walk after p steps, or you can do some kind of an infinite random walk, and then you get a regularized Laplacian, and so on and so forth. So this is different ways by which you can compare nodes in a graph. Now let's turn to the question of, I want to apply similar ideas or similar kind of intuitions that I had, and I know that there's a rich variety of things that I can derive to compare nodes in a graph or to penalize variations of a function on a graph. Can I apply some of those ideas to compare two graphs? So if somebody gives me two graphs, say protein molecules, and then says, okay, compare them and tell me how similar they are, can I do the same thing? Again, I go back to the same old idea and I say, okay, why don't we just go and count the number of matching walks? And then again we saw that you can't just count the walks, you have to somehow discount them. And then the basic idea is that two graphs are similar if they have a lot of if many walks are matching. But again, I've been very fuzzy, right? So, sorry, this must be 3 questions, or I forgot how to count. But they're basically 3 questions that you must be thinking about, right? Which is natural to think about. How on earth are you going to formalize this intuition? What is the meaning of a matching walk, first of all? The second question is that, okay, even if you can formalize this intuition, can you actually go ahead and compute this beast efficiently, right? We, of course, in the end of the day, we want to run them on our machines. And the third thing is that how is this whole idea related to diffusion kernels? I mean, I brought up this whole story of diffusion kernels, and where is the relation coming from? So the rest of the talk, I'm going to answer these 3 questions, essentially. If there are any questions, please feel free to interrupt me at any point. Yeah.
So are we going to assume that we have an alignment between the nodes of the 2 graphs?
Yes, essentially that's what. But you will work with all possible alignments. That's what we would do next. That's what we're going to do next. So you're spot on with the intuition that we have this notion of an alignment, and but because we are sort of not given the alignment a priori, we have to figure out under all possible alignments or under all possible identifications how things would match up. So for doing that, basically I need the notion of a direct product graph. So graph theorists, so for a long time this is kind of an interesting thing for me to discover, because initially I just thought there was only one product graph, and I always thought product graphs means this. But then I went to a graph theory conference, and then people said, oh no, there are 4 different notions of product graphs, and gave me this one Hungarian book on book written by 2 Hungarians on these 4 different product graphs, and I was kind of educated, and I realized that this was what they call the direct product graph. So the direct product graph is a very simple graph. Let me illustrate it with an example. Basically what you do is for every pair of edges, for every pair of nodes in your original 2 graphs, you have an edge in the product graph. So for instance, 1, 1 prime, you would have an edge. 1, 2 prime, you would have an edge somewhere. Where is it? Yeah, 1, 2 prime, and so on and so on. So for every pair of edges, you would have, for every pair of nodes, you would have a node in the product graph. And then you would connect 2 nodes if and only if the corresponding 2 nodes are connected in the original graph. So for instance, you see that 1, 1 prime would be connected to 2, 2 prime, because 1, 2 and 1 prime, 2 prime are connected in the original graph. So it is like saying if 1 is in correspondence with 1 prime and 2 is in correspondence with 2 prime, then R is 1 connected to 2 and 1 prime connected to 2 prime. So this is the key notion of correspondence. You can already see that in some sense what this correspondence does is it captures under all possible ways in which you could map, say, 1 to a vertex from here to a vertex in this graph. There is a corresponding node there, and then if that under that correspondence, if there is an edge, then there is an edge in the product graph. Right? So this is kind of the intuition. And if you carry this intuition forward, you'll and just think for a while, it's very easy to realize that if you do a random walk on the product graph, then essentially you're doing a simultaneous random walk on the 2 original graphs. So in other words, if there is a random walk on the product graph, there is a corresponding set of correspondences under which you can do a random walk in the original graphs. So this is a very key insight, and this allows you to take all possible correspondences into account simultaneously and then do a random walk. And now again you can do the same thing. You can, for instance, normalize on the size of the graphs. You would have some kind of decay factor, and then you would sum up over all possible weights. So this gives you a kernel, and the kernel is just defined to be the X of the adjacency matrix of the product graph. Right? The key, the cool idea is that, again, this is you're not restricted only to the X function. You can take any of the other functions that I talked about, and so the entire machinery of this regularization on graphs now comes to bear, and you can apply them to your problem based on how you want to regularize things and so on. And turns out that, not surprisingly, many people have done this, and they have come from completely different approaches. and essentially have discovered or sort of rediscovered these things. And two things that the two that I'd be particularly interested is the X, which is sort of comes from the intuition of diffusion, and the other one that I'm very interested in would be these notions of what are called geometric graph kernels or geometric random walk kernels. No, sorry, these are called the random walk kernels. So here what happens is that you, instead of doing a lambda to the k over k factorial decay, if you just do a lambda to the k decay, and again you have to choose lambda appropriately based on the spectrum, then it turns out that you can just write out the geometric series, and then you would have to invert this matrix, right? And then sum over the entries and then normalize. You might say, oh, why do I want to just sum over the entries of the matrix? Why can't I do something more clever? Yes, of course you can, by just taking expectations. So you can just have some kind of an initial distribution of starting and an initial distribution of stopping. So you can ask at every point of time what's the probability that I'd stop my random walk at this point. So if you have qx, which is the stopping probability on a vertex, and px, which is the starting probability, the initial probability, then again you can do essentially take expectations. And this is what the people do, and they call these the marginalized graph kernels or the marginal graph kernels.
Can you extend this to weighted edges?
Sorry?
Can you extend this to weighted edges?
Yes, yes. You can do extend them to edges too.
Perhaps in some situations, the sum is not the inverse of functions.
You can't invert. Yeah. So you.
Not the inverse.
Sorry?
I mean the sum.
You mean the invert? Yeah. You cannot invert this matrix.
No. Because you use matrix A.
Yes.
The eigenvalue of the matrix A is from 0 to 2.
Yes.
You could look for the inverse as the eigenvalue is from 0 to 1.
No, A itself doesn't have.
Absolute eigenvalue of A should be less than 1 if you wouldn't get an inverse.
Yes. See, the thing is that A itself is not a normalized matrix, and yeah, you're right. For this inverse to exist, there must be you need to have conditions on the spectrum. Either so that's why I said lambda has to be chosen appropriately. Basically, it is not A which has to have bounded spectrum, but lambda times A which has to have bounded spectrum, and that's what basically the condition would be essentially 1 over. Lambda must be smaller than 1 over the largest eigenvalue of A. This is essentially the condition that I'm hiding, but yeah, you need that for the inverse to exist. But now it is all nice. We kind of got around to defining how the graphs could be compared, and we could also do some fun stuff of defining kernels. But then you have a huge problem, literally, because if your product graph has each have n vertices, then you have a pair, for every pair of vertices you have a vertex in the product graph, so which means that you have n square vertices in the product graph. And if you look at the adjacency matrix, then the adjacency matrix is a huge matrix, n square by n square matrix. And now if you want to invert an n square by n square matrix, it's an order n to the 6 effort. Or if you want to take the exponentiation, again it's an order n to the 6 effort. So this is kind of all nice, but doesn't look very scalable. Turns out that there are okay. So before we launch into how we can compute this efficiently, note that these adjacency matrices are not arbitrary n square by n square matrices. They have a very, very strong, nice structure, and so somehow if the whole idea that I'll present now is basically to take advantage of that structure and to show that this structure is useful. So the way I do that is that before I do that, I need to introduce this notion of a canonical product. You can already see where it's going. Basically, the canonical product will be the adjacency matrix of the product graph will be the canonical product of the adjacency matrices. So this is where it's going. But just bear with me as I go through the definitions. So basically, if I give you two matrices A and B, then taking a canonical product is very simple. What you do is you take B and you repeat you multiply that element of A and you repeat that whole matrix here. So there's a whole block here of B multiplied by 1, so the B repeats itself. Whole block of B multiplied by 0, so you get a 0 block. Again, whole block of B multiplied by 0, 0, whole block of B multiplied by 1, 1, and so on and so on. So this is like a huge matrix, and you can of course see that if this is an n by n and this is n by n, then A crown B is an n square by n square matrix. So this is like repeating patterns of the matrix all over the place. And again, the next key insight which allows us to compute things efficiently is the fact that the adjacency matrix of the product graph is nothing but the Kronecker product of the adjacency matrices of the graph. It takes a bit of time to convince yourself of this, but once you start thinking about it, it's very clear. You just have to go back to the definition of how you define the adjacency, how you define the product graph, and also how you define the Kronecker product, and you can show that they're exactly the same. Now, if you want to compute the x of this big large matrix, there's a very nice theorem which says that just taking the x of the big matrix is equivalent to computing the exponential of the smaller matrices and then taking the Kronecker product. So you can either do the Kronecker product of the big matrix or do it of the small matrices and then put them together. And of course, x of an n by n matrix is order n cubed, and so you can reduce the overall time to order n cubed. But if you want to do similar trick for inverting this matrix, a little bit more work. And that's again what I would want to concentrate on. So to do this, I need to introduce you to something which is basically from control theory. People use this in control theory and they call it the Sylvester Equation. In fact, it's so widely used that if you look at the control theory toolbox of MATLAB, it has a method to solve it. It's called DILAP. It's called dynamic Lyapunov equation. So there are different names by which it's known. One of them is a Sylvester equation, the other one is that it's a Lyapunov equation. It's basically a funny looking equation where x is the variable that you're solving for, and you're given three matrices P, A, and A prime. There are three different three different matrices that you're given for, and you want to solve for x, and then there are various incarnations of this. This is like a single-sided Sylvester equation. Then you can have a double-sided Sylvester equation, and so on and so on. But for this talk, basically, I just need the simple form of the Sylvester equation. And in fact, they are efficiently solvable in order n cubed time, and they're in fact public domain codes that do the same thing for you. And so what I will do is I'll show that if you can solve the Sylvester equation, then you can compute the inverse of that matrix, and essentially you can compute the graph kernels that you need efficiently. So this is how the reduction will go. But before I actually show that and show you one slide which has a lot of gory math in it, and which you'll have to bear with me for, I want to show you something else that people use in Cron algebra. Is this very nice operator called a Veck operator. So a Veck is a linear operator which you can think of as flattening a matrix. So you take a matrix, you stack up the rows of the matrix, and you get a vector out of it. So basically here is the matrix, so you just stack up that row, column, then the third column, and the third column. And this is an extremely useful and extremely powerful formula, which is very well known to people working with Kronecker products. Is this thing that if you take the product of three matrices and then take a Veck, it is equivalent to first taking the Kron of A and C and then applying it to Veck. Right? So this is an extremely useful and important formula that people use, and this is what we will use. Yes, it's true for arbitrary BC. I mean, you have to have conforming dimensions, but that's all. And now, how do you actually show that? Computing the graph kernels and computing the Sylvester equation are related. Basically, you have to bear with me, this is my densest slide. So basically you take a Veck operator and you apply it on both sides. Veck is a linear operator, nothing happens. You can apply it freely on both sides. Then you take this part and you apply the key equation to this part, and it factorizes out as a cron a prime in Veck x. You take this on the other side and you rearrange, and now basically Veck of x, which is the solution to a Sylvester equation, is nothing but the inverse of a cron a prime inverse with p. So now if you set p to be such that p of x is essentially the Veck of this capital P, then what you have computed by computing x and taking its Veck is essentially what you wanted. This is the adjacency matrix of the product graph, the inverse, and then p of x, and you multiply it with q of x, and multiplying it with q of x, which is an n square by 1 vector, is an order n square operation. This thing you could compute by using the Sylvester equation, the solution of the Sylvester equation. That's an order n cubed operation, so overall the kernel can be computed in order n cubed time. So this is the key trick. But it's still kind of unsatisfactory, because order n cubed in the worst case is all fine, but you know that in real life basically the graphs are never that dense, and you still don't want to do n cubed. And if you work with a large sparse graph and I tell you, well, here's an order n cubed algorithm, most of you would laugh at me. So how do you do this more in practice? The first thing you observe is that in practice, if you have a really large graph, most of the graphs are never sparse, or never dense. So most of the times, if the graphs are really large, most of the times they're sparse. So what you do is, the first thing you realize is that if you look at the Veck ABC formula, there is in some sense an inherent computational mismatch on both sides of the formula. This is one of these few formulas, if you look at a linear algebra formula, most of the times you'd see there's a computational match, right? I mean, if you look at the left hand side, it takes the same time to compute as the right hand side. Here there's an inherent computational mismatch. The inherent computational mismatch is that if you compute the cron first and then do a multiplication with the Veck, then this is an order n4 operation, because the cron is an n square by n square matrix, and then you are doing a multiplication with an n square by 1 vector. On the other hand, if you take the product of these three matrices and then take a Veck, the product is of course order n cubed, and then you can apply a Veck, which is an n square operation, and you still have order n cubed. So in some sense there's an inherent computational mismatch on both sides of the equation, and you can exploit that. So basically, to invert a linear system, most of the times if it is sparse, people would say use CG or use fixed point, one of the two. Here you can do slightly better than that. You can say, yes, I can of course use CG or a fixed point, but when and basically CG would ask me at every point of time to take this matrix, and it will give me back a residual vector and say multiply this matrix with this residual vector. And I can do this cheaper than a naive computation. So I can do this, I can save order n effort here already. And if the spectrum is nice and the matrix is sparse enough, then I can do this much faster. The same way I can also solve for a fixed point of the solution. Again, the convergence of the fixed point depends on the spectrum. It depends on how bounded your eigenvalues are. And if your eigenvalues all need to be smaller than 1, and depending on how much the gap is, you can decay faster and you can get to the solution. So there are two different ways by which, and the CG of course depends on the effective rank of the matrix, how much the real rank, the number of distinct eigenvalues. Now, and then to answer the last question, all these things were nice. I could port many of the things that I used from the regularization theory to do random walks, but what about diffusion? It turns out to be a much more tricky question than you'd imagine, because one way to think about it is as follows. So the first thing that happens is that if you take the Laplacian of the product graph, of the direct product graph, then it is not the Laplacian, it's not the cron product of the Laplacians. And this kind of, after a while, starts to make sense, because in some sense the direct product graph is one where the random walks sort of decompose. Diffusion is a continuous time limit of the random walk, And so diffusion need not decompose on the same graph, on the product graph. So in general this is not true. But this was one of the nice things of going to the graph theory conference, was that I learned from the graph theorists that there is another type of graph product, which is the one where both random walks and diffusion decomposes, and that is what is called a Cartesian product of graphs. A Cartesian product of graphs is exactly what you'd expect if you think of one graph along one dimension and the other graph along another dimension. Just think of a chain graph, and if you take a Cartesian product you would get the grid. So, and basically what happens is that, or another way which I sometimes used to think of it, is that you take one graph and then you replace every node in that graph by a copy of the second graph. So this is another way to think of the Cartesian product graph. So you just replace, and then again you have to think about this. This took me quite a while to kind of convince myself that this is the right graph on which diffusion factorizes. So if you do the continuous time limit of a random walk, diffusion factorizes on this graph. And again it turns out that the adjacency matrix of the product of the Cartesian product graph can be written as basically in terms of canonical products with an identity stuck in the middle, essentially. And then the good news is that all the efficient computational tricks that I showed you apply. I mean, there's a little bit of, you have to keep track of indices, and things grow because a to the k, now you have a binomial series instead of just a normal single series. So the math gets a bit more messy, but essentially all the tricks apply. And I must say that I don't have any real experiments to report on the diffusion kernels. Hopefully Carsten is beavering away at them right now as we speak, but this is a very new idea, so I don't have experiments to report on that. And so to test this whole thing, our aim here in all the tests here is not to worry about efficiency in the machine learning sense of how does it do on a test set and so on. Our aim is just to show that you can compute these things much faster. That's where we are going for. So there are two types of scaling behavior that we studied on synthetic graphs. One type of scaling behavior is how does it scale with the number of nodes. In some sense, if you're a computer scientist, you would laugh at this plot and you'd say, well, you have proven things in the order notation, what do you need more? But if you're a practical person, you'd care about this, right? You'd want to know the constants, you'd want to know how it actually performs. So basically what we did is we started with empty graphs, and then we randomly kept on inserting edges until we got certain degree of fill-in the graphs. And then we'll repeat this process a few times, and then you'd have a set of 10 graphs, and then you'd just compute the kernel on these. You'd compute the 10 by 10 kernel on this graph. And so here is how basically the red dotted line shows you order n6, so behavior, and the black line, black or blue, whatever it is, shows you a order n cubed behavior. And of course, as you expect, initially this is kind of like noisy stuff because I think most of the things might be happening in cache and so on, but it's only after some reasonable size that you actually start seeing the true behavior. And as expected, I mean, of course, the direct method, which is by inverting the matrix explicitly, scales as order n6, while our methods to order n cubed. But to also investigate what happens when really you look at sparse graphs. I mean, I made this claim that you can actually work with sparse graphs, and then with sparse graphs you'd get much speed up. This is actually a slightly misleading plot because we work only with graphs of size 32 because we wanted to show this direct method. I also have other plots which I don't have in this talk, but where we only compare these methods, and then you can clearly see that basically the CG and the fixed point methods can exploit sparsity quite well, and when you have sparse graphs they perform much so the constants are much smaller, and they actually do much better than the Sylvester solver in this case. But again, the idea here is that you start with a fixed size graph, but instead of changing the size, you change the fill-in. So you look at what happens when you start filling in things. And you can see in the other plot, I should have put that in actually. In the other plot, you can actually clearly see that the Sylvester equation sort of remains constant for all degree fill-ins because it can't exploit structure in the graph. But if you look at the fixed point and the CG, they actually are very fast when the graph is sparse. But then as it becomes denser and denser, they become more expensive. Yes.
There could be many policies based on which you would grow the graphs, right? So basically various types of power laws and so on.
Yes.
So how do you think how sensitive these results are to the actual?
To the distribution, to be honest, I don't know. We haven't tried by. So a real good test would be that we actually take a model like one of the small world graphs or a random graph model and then test it on them. But at least just randomly inserting at uniform the edges, it seemed to be reasonably immune to that. But yeah, you're right. I don't have experiments for that.
These experiments with the two graphs having the same number of nodes each.
No, I mean we have those are synthetic experiments. In the real experiments, that's not true, and we'd have some real experiments going ahead. Then the other thing we just wanted to check was that does the Veck trick actually help you? I mean, this is an obvious thing to do. So we just did basically the fixed point iteration without the Veck trick and then the fixed point iteration with the Veck trick. And this is kind of interesting because in the original paper on marginalized graph kernels, they essentially did not talk about the Veck trick, and so they just did. That's what I mean by original. This was the original marginalized graph kernel paper, and then once we did the Veck trick, we got more speed ups. And then these are some semi-real experiments, which is where you looked at unlabeled graphs, and there are three different data sets where I think MuTag and PTC are essentially chemical compounds which are modeled as graphs. These are again small data sets, and then there's this enzyme and protein data structure which is I think about 1,200 or sorry, it was 2,000. I don't quite remember whether it was 2,000 or 2,200 or 1,200 number of graphs, and this is basically a protein database modeled as a graph. So you have a certain way of inserting edges and nodes in the graph. Basically, the nodes are all secondary structures, and then you connect things up if the secondary structures are close to each other physically or are close to each other on the protein sequence. And then again, you can see that. If you just do the Sylvester equation method, almost always, especially on large graphs, like in the protein case, it turns out to be much more expensive. And it's kind of you can also see that in some sense, as in real life data sets, as the graph becomes larger and larger, it becomes sparser and sparser as well. I mean, there's generally not that many data sets where you have large and dense graphs. And the Sylvester equation solver really doesn't know about how to exploit sparsity internally. It just munges away at whatever structure that you give it, while the fixed point and the conjugate gradient solvers actually can exploit sparsity.
Can you just give a quick one-sentence description of how you actually use these kernels to do the molecular function prediction?
So basically, this gives you a valid PSD kernel, and then you plug it into an SVM, and then you do.
Do you have some labeled examples as a classic?
Yeah, you have some labeled examples, but here I'm just focusing on the runtimes because people were but it's just a usual stock standard thing. Again. I didn't talk about this much, but basically what happens is that you can also work with labeled graphs. So labeled graphs can have two types of labels. You can have labels on the nodes, or you can have labels on the edges. And in fact, you can do one step better. Instead of just having labels and comparing them, you can have some kind of a kernel which compares the labels. So you can have another measure of similarity which just compares the labels, and you can put that in, and the whole framework actually works still. And these are again results with labeled graphs. There are a bunch of things that I didn't talk about. I mean, in some sense, I kind of only gave you a flavor for what sort of things we do there. There's a enormous amount of things that I did not talk about just because I wanted to make this more accessible to a wider audience. First thing is that random walks need not be only defined on the plus dot semi-ring that you're talking about. So in a plus dot semi-ring, you multiply two numbers, you add them up in a normal way. You can also do a random walk on a min plus semiring. So for those of you who are not familiar with semirings, a semiring is a ring which lacks negation, or another way to think about it is a generalization of the plus dot operators. So any two pair of operators which behave like the plus, so they must have distributivity, associativity, and must have an additive inverse, and must have a multiplicative identity and additive identity. They constitute a semiring. So you can also do semirings on so you can do random walks on other semirings. So when and one way to think about it is that if you do a random walk on the min plus semiring, then essentially you're computing the shortest path between two vertices. So this is for again people who do HMMs or CRFs, this is the key difference between Viterbi and Baum-Welch. So Baum-Welch and Viterbi are duals of each other, except that one is done in the plus dot semiring, the other is done in the min plus semiring. It's the same thing here. So you can also do a random walk on a graph with the min plus semiring, and you'd get Dijkstra's, which is essentially Viterbi applied on a graph. But then there is a bit of problem. Min plus by itself doesn't give you a valid positive semi-definite kernel. I mean, there's some theory to show that. There's also some subtle differences that I didn't mention about when you should use the adjacency matrix, when you should use the normalized version, the Laplacian, the normalized Laplacian, and so on, and how those things change the admissible set of lambdas, so on, the decay factors. I didn't talk anything about that. And then, of course, I briefly mentioned this, but you can also have kernels on vertices and kernels on edges. So you can have different ways to compare kernels on edges. And there is also an extension of this, this happened before. I mean, this is kind of ironic, but this happened before, and I actually have a paper in IJCV on this, and while I'm still working on the graph kernels paper. But there are extensions of these when you want to compare ARMA models. So in ARMA models, think of them as you have a hidden state that is evolving, and then you have an external state, the observed state, that's also evolving. And so essentially the same kind of ideas would work there. So you look at what is at what is evolving that is visible, and then you would integrate over all possible ways in which your system could evolve. And again, it turns out that you can compute these things efficiently. And this is again work with joint work with René Vidal and Alex Mola. And there is a big general purpose theory which is sort of the mother of all theories, works for ARMA models with arbitrary semirings, and this notion of a Binet-Cauchy theorem which gets into this really abstract space of using operators and Fredholm operators and so on. So if you're interested in that kind of a thing, then look at my NIPS paper. This is a joint work with Alex Mola. And this is again something that I did recently, which is very interesting. Is for those of you who know about some recent work by Corina Curtis, Marier Mori, and Patrick Hafner, they talk about some things called rational kernels. So rational kernels are ways to compare two transducers. So transducers are much more general objects than graphs, but it turns out that if you sufficiently if you look at rational kernels and specialize them to graphs, you exactly get random walk kernels. And that was kind of very neat to see that basically the rational kernels and random walk kernels are exactly the same thing, except that rational kernels are sort of making them more general and putting them onto transducers. And of course, this is my favorite sentence, that every discrete kernel on every kernel on discrete objects is essentially related to the R-convolution kernels of Hostler. I mean, they're all. I mean, R-convolution is this big framework, and almost everything can be hung up from that. So it's this beautiful theory by Hostler. And so, in some sense, to me, this was kind of the first time I could see connections between all these 4 different streams of research that was happening in graph kernels, and often it was presented with very different motivations, and so I couldn't really understand where the connections were, and this was fun to do, to understand the connections between these various fields. I mean, diffusion kernels, this regularization on graphs, geometric and random walk kernels, and the marginal graph kernels and of course also I should add rational kernels there. And I showed you a way to efficiently compute them by exploiting Kronecker products. And it turns out that when you have kernels on the nodes and the edges, basically you have to reinvent linear algebra in an RKHS. So essentially you have to reinvent tensor algebra to make this whole thing work, but and to show that it's positive semi-definite and so on. But that was fun. We had some fun doing that. There are a bunch of papers that you can go to my homepage and download. And one, I want to leave you with a big open question that sort of troubles me on and off, is that I showed you a way of comparing two different graphs by comparing paths or random walks in the graph. Right? So this is a polynomial time algorithm. I showed you how it can be done in order n cubed. On the other hand, you might say, oh, why in the first place didn't you just start with the two graphs, look at all possible subgraphs of the two graphs, and then just compare them, right? You could have just taken all possible subgraphs and then just compared them and said if two graphs have a lot of subgraphs which are common, then they must be similar, and if not, they must be dissimilar, right? This seems like a natural thing to do. The problem is that this is NP hard. In fact, you can show that if you can compute such a kernel, so if you can compute such a similarity metric perfectly, then you can solve subgraph isomorphism. It's in fact harder than a subgraph isomorphism. But then you say, okay, well, subgraphs might be too hard, arbitrary subgraphs are okay. You worked with a special kind of subgraphs which are paths. Can't you do something better than that? Can't you do something intermediate? Can't you do even simple paths? I allowed repetitions in, you can repeat a vertex in the paths that I looked at. Can you do a simple path where no vertices repeat? Can you do that in polynomial time? Turns out it's very difficult. At least I don't know of an algorithm to do that. Can you do cycles? Can you do trees? Anything between an arbitrary graph, subgraph, and the simple paths seems to be hard. And the moment you change your complexity from paths to something else, immediately the complexity jumps up. I mean, you'd intuitively think, oh, paths are easy. The next step would be trees. Can we look at all possible spanning trees and somehow do this? Turns out to be very difficult. And we seem to lose polynomial runtime. So the question is, are there classes of graphs for which certain subgraphs are efficient, or are there even certain classes of subgraphs for which you can do this general purpose efficient algorithm? And this would be something that I have no answers about, but I would love to hear if you have any insights. Yes?
Would many approximation algorithms exist? It seems like it would really, it's calling for approximation algorithms where you would do various sampling.
Yes, so if you talk in terms of complexity theory, basically graph isomorphism itself is between P and NP. It's in a class of its own. It's not known to be NP, and neither is it known to be P. But subgraph isomorphism is known to be NP hard. So, and for graph isomorphism, there are lots and lots of efficient empirical algorithms. I mean, when I mean empirical algorithms, there's a guy in ANU, in fact, Brendan McKay, whose entire life is spent on developing this package which he calls Naughty, N-A-U-T-Y, and the whole aim of Naughty is if you give two graphs, it will tell you whether they're isomorphic or not. So it has like this series of rule-based tests built into it. So it just applies them one after another, and at some point when it cannot, I mean, when a graph fails a test, it says they're not isomorphic or isomorphic, whatever it is. So it can only give you, I mean, in the end, it just keeps doing brute force. So, but
proving approximation bound is very hard, or impossible.
Yeah, I mean, I don't even know where to begin with proving approximation bounds, to be frank. I mean, I don't even know. And the other important thing that happens is that eventually you want to plug all this into a machine learning algorithm. So just an approximate algorithm might not give you a positive semi-definite kernel, right? So that's a major issue. So I mean, if I knew that, yes, I had an approximation algorithm which is also guaranteed to give me a positive semi-definite kernel, then sure. And finally, here is a set of papers. I mean, there's a bunch of journal papers. This one is still under preparation. I mean, it's pretty close to being submitted soon. There's the IGCV paper, there are a couple of NIPS papers, and then there's some applications to bioinformatics. There's an ISMB paper, there's a PSB paper and so on. So sorry? Sorry, I didn't get your question. Pseudo's work on?
Yes, Pseudo also work on graph classification issues.
Yes.
And he uses subgraph as a feature.
Yes, but he uses this boosting type thing, right? He uses this subgraphs in some kind of a boosting.
Each graph as a set of subgraphs.
Yes, but I don't think he can handle all possible subgraphs. He only
just select some subgraphs.
yeah. So he has this. So what he does is some kind of a I don't remember the full details. I've seen this work, and basically he, instead of doing this set of all possible subgraphs, he selects some subgraphs by the last time I talked to him, he was doing some kind of boosting to select those subgraphs and then use them. But I don't think he can. I mean, of course, it's NP hard to do the subgraph isomorphism exactly.
So if you only consider similarity between two graphs,
Uh-huh.
so you can select subgraphs, feature, and then compute.
No, but what I'm asking is a stronger condition, right? I'm saying so what Suda-san is doing is basically he takes all possible subgraphs, but then he selects only some of them, right? As in, he just selects out of the set of all possible subgraphs, he weights them to give high weights to certain graphs. What I'm asking for is that given any arbitrary graph, can you represent, the feature representation is the set of all trees or the set of all cycles or the set of all simple paths in the graph, and then can you take a dot product? And that seems to be difficult.
Could you do something like assisted sampling? So similar to LSH techniques where...
So I do that. So I have a paper where I do that. This is a recent paper where basically what you do is, this is sort of inspired by a algorithm by a theorem which is known as the matrix reconstruction theorem, which says that if you give me the set of all principal minors, so a principal minor is you cut off one row and one column from a matrix, and if the matrix is originally of size larger than 5, I think, yeah, larger than 5, if you give me the set of all principal minors of this matrix, I can reconstruct the matrix. So there's a theorem, it's called the matrix reconstruction theorem. And so basically we kind of said, which doesn't immediately imply, but sort of has this flavor that, okay, if I tell you all possible 4x4 sub matrices of a matrix, you can reconstruct it with a high degree of confidence what the original matrix was.
That's the form of the graph reconstruction conjecture, right?
Yeah, that's the graph reconstruction conjecture. For graphs it's harder, for matrices it's easier. Because for matrices you have a fixed order, while for graphs you have you get the exponential. So this is Tute's big question in 1967, where he says, if I give you the set of all 4 subgraphs of a graph, can I reconstruct? But it turns out that if I just do a simple thing of just representing a graph by its set of all possible 4 size subgraphs, that alone is sufficient generally to say many things about the graph. So if this, especially in biological networks where you have this large protein-protein interaction networks and you want to compare them, just taking all 4x4 or 5x5 subgraphs, but even there, just doing a naive approach of listing all the 4x4 subgraphs is order n4. But we have a efficient sampling algorithm which which converges exponentially fast in like linear time or something. I mean, it's like you have to do something like 5 times the number of nodes. You have to draw 5 times the number of node samples, and that gives you a distribution that is pretty close to the optimum. So we tried some of these things.
Another question. So here the similarity between graphs is based on kernels and operators. So you also mentioned the kernels depend on edges. Do you have any techniques with the kernel on edges?
Kernel on edges? Basically, you just have labels on the edges, and then the kernels on the edges are the kernels between the labels. So, for instance, if let's just say, for example, you're representing a molecule by a graph, right? and then you have edges which are bonds between molecules, then you might say, you might have some notion of which bonds are more closer to each other than which bonds, and then that's a kernel. Sorry? Oh, if you have no labels, you just work with the so-called delta kernel, right? You just say if there is an edge, then it's 1. If there's no edge, then it's 0. So that's basically the idea.
Okay.